Okay, Jianhong, you can start whenever you like.
Right, thank you. Good morning, everyone. Thank you for coming to this regular session of the Fields Institute seminar on COVID-19 mathematical modeling. I'm very pleased today to have Professor Choi Day from Queen's University. Choi is a professor of mathematics and biology. Is one of the most prominent figures in the general field of mathematical biology. In the field of emerging infectious disease, Choi was heavily involved with modeling to inform and assist public health decision-making from both the 2003, 2004 SARS pandemic to 2009-10 flu influenza pandemic, and more significantly in the COVID-19 pandemic. And actually, Kuma is here, staying a sabbatical from his vacation. And on behalf of Choi, on behalf of the Fields Institute, on behalf of Kuma, so I would like to thank you again, Choi. It's your time.
Okay, thanks, Jianhong. So good morning, everyone. I'm going to share my screen on my iPad, so I'm going to disappear myself here. Just one second. Okay, I assume everybody can see that all right. So I'm going to talk about some work today that's joint work with David McAdams, who's a professor at Duke University in business and economics. And the title that I originally gave was The Political Economy of Infectious Disease Outbreaks. I've shortened it here just to the economics of disease outbreaks. The idea is basically to use some modeling to examine the economic factors that influence people's decisions over the course of an outbreak, as well as maybe the political or other motivations of government leaders when they act on these wishes of their constituents, I guess you might say. I guess I'll start also by making a couple of caveats. So this is obviously work motivated by the current COVID outbreak, but I want to stress that it's not a model that is specific to COVID. It's meant to be a very general but very stylized model in some ways. And so it should, you should keep that in mind when I'm presenting the results. I'm not intending to make very detailed or quantitative policy recommendations or predictions for COVID, but rather I want to use a relatively simple model to draw out some general qualitative insights about how people's incentives driven by economic factors change over the course of an outbreak. So there are four parts to what I'll talk about. I'll give a bit of a background to set the stage for the story. I'll say a bit about the model setup here. I'll go through some of the analysis, and then just a brief slide or two summarizing things. So I'll start here with active cases. This is a plot. So first, I guess a couple of things to point out. This is a plot, a log scale on the vertical axis here for a number of different countries as a function of time on the horizontal axis. And the other thing to note is on the horizontal axis, each country has been translated horizontally, so they all line up at more or less the same point in time. So you read the horizontal axis as time since there was at least 20 active cases in each country. Canada is the black line here. You can see we're sort of a middling country in some sense. We've done better than a number of other places, but not as well as some other countries. Of course, this is not corrected for by population size either, but just as a bit of context to see where we fall out. These lines here are the different slopes you would expect under different patterns of exponential growth in terms of doubling time 2 days, 3 days, 4 days, etc. So you can see we were initially undergoing exponential growth, linear on a log scale here with a doubling time of about 4 days, and then things turned and we've sort of flattened the curve, as they say. And one of the main reasons for that is because of the massive reduction in mobility that people have basically undertaken, both because they've been asked to, and I think partly because of their own free will. So this is plotting data from cell phone mobility data, I guess. So the vertical axis here is the percentage of time a person's cell phone checks in near their home, and the horizontal axis is date, obviously. This point in time here, March 14th, is basically when the large-scale shutdown in Ontario started to happen. So prior to that point, you can see that, and these dashed lines here are weekends. So you can see that prior to that point, there's a lot of people at home on weekends. It's low during the week, it's high on the weekends, low during the week. And then we instituted this big shutdown, and then it kind of stayed high. People were staying home for most of the time from that point onward. And this has had an enormous consequence in terms of the generation of new infections. And to sort of illustrate that, I've overlaid on this plot that same mobility data with this curve here now, which is the case count for Ontario only. So again, here's the exponential growth phase, doubling time every 4 days initially. This is where we instituted the big shutdown, if you like, and there's about a 2-week lag between when we introduce any sort of control measure and when that shows up in the data, just because of the life history of the disease. So you can see from when it was instituted, 1 week, 2 weeks, that's where you start to see this leveling off happen. So pretty suggestive, if not kind of definitive in some ways, that this massive reduction in movement and interaction has had a huge effect in slowing down the spread of COVID. Now, my interest in this talk is talking about people's incentives in terms of what they're going to do with physical distancing. And the first thing I want to point out is that physical distancing is a game in the game theoretic sense of the word. And to illustrate that, I've just got a couple of examples here, one epidemiological and one economic. Epidemiologically, it's a game in the sense that other people's choices of their behavior will affect the incentives for my choices. So many of you, probably all of you, are staying home from the office right now, in part to control infection. But given that everybody's away from the office, there isn't actually much risk in me going into the office. In fact, I'm in the office today. So I'm sort of a cheater, if you like. We're supposed to be staying home, but I'm in at work. But if everybody followed that incentive, then everybody would end up at work. And there's sort of a problem that you could imagine arising from that as a result of increased spread. So there's a game aspect to the epidemiology. There's also a game aspect to the economics, because, for example, if I own a restaurant, my incentive to stay open is a lot higher if there are lots of other people out active in the community, because there are people coming to my restaurant. If everybody's already staying home, then my incentive to stay open is much reduced. And so there's a game there as well, in terms of typically, or often anyways, we would have a positive benefit economically for other people being out, sort of a complementarity to people's actions that way. And you can think of this both financially and in terms of just your personal enjoyment. If you're going to a restaurant, you would probably enjoy it more if you're going there with other people. So that's what I mean by a game. And I'm going to talk about specific games, because it turns out that specific games arise over the course of an outbreak. And there are these 4 particular games that I want to highlight here, because they're going to be important in the results I'm going to present. So to just sort of walk you through this, these are just simple examples where I'm imagining a game where you're playing against a single opponent. So your behavior is on the vertical here, and your opponent's behavior is on the horizontal here. And you each have 2 choices. You can either go to work or you can stay home. And the numbers in the matrix tell you your payoff as a function of what you do and what your opponent does. So in this trivial game, for example, if your opponent stays home, there are your 2 choices. You can stay home and you get a payoff of 0, or you can go to work and you get a payoff of 1. So clearly, if your opponent stays home, your best choice is to go to work. If your opponent goes to work, that's where we look in the table now. If your opponent goes to work and you stay home, you get a 1. If you go to work, you get a 2. So again, it's in your best interest to go to work if your opponent goes to work. So assuming the game is symmetric and you're both playing this is where we're going to end up. Both of us are going to go to work because we prefer to do that no matter what our opponent is doing. And we end up at work. And the other thing to notice is that we end up at work and we collectively get a payoff here of 2, which is better than we would have if we'd stayed home, which would have been 0. Now let's contrast that with what's down in the right-hand corner here, which is the prisoner's dilemma game. So here I am again making my decision. If my opponent stays home, I'm going to want to go to work because 4 is bigger than 3. If my opponent goes to work, again, I'm going to want to go to work because 2 is bigger than 1. And so again, since the game is symmetric, we'll both end up going to work. And so we'll end up getting a payoff of 2. But notice that if we had somehow managed to collaborate or cooperate and both stay home, we could have been here and we both would have got a payoff of 3, which would have been better for both of us. But of course, it's always open to cheating, where if we're both staying home, one of us might then go to work and cheat and get an extra payoff. And it's this sort of prisoner's dilemma that's going to be important in the results I'm going to talk about. And it's a government leader's intervention that can do things like move a system from here, where we'd end up if everyone acted in their own self-interest, to somewhere here where we wouldn't have ended up there by self-interest, but it's collectively a better place to be. The other 2 games on here, I'll just quickly point out. The coordination game is kind of like it sounds. So again, if my opponent stays home, I want to stay home now. If my opponent goes to work, I want to go to work. So basically, you end up in one of two places, either of those places there. And it's a coordination game because basically you do best by doing whatever everybody else is doing. And the sort of opposite in some sense of that is the diversification game, where down here, if my opponent stays home, I want to go to work. And if my opponent goes to work, I want to stay home. And in that case, you can imagine that if a bunch of people playing this game, we're going to end up with some sort of mixture of people playing each of these two strategies. And that's why I've called it a diversification game. This is sometimes also called a game of chicken. Okay, so those are going to be important in the results that I'm going to present. I'll just tell you a bit about the overall model structure before I get into the details. So I'm going to consider a model where you have a population of citizens. I'm going to call them agents. And they're each acting individually in their own personal interest. And they're choosing whether or not to distance. There's going to be a binary choice, yes or no. The population is assumed to be big enough that any agent's decision isn't going to have any significant effect on the overall epidemiological dynamics. And I'm going to suppose that there's a government leader who can compel the agents to act in a coordinated way, and they would do so if it's in those agents' interests. So that's the incentive of the government leader that I'm going to assume. You can imagine other incentives as well, but that's probably not a bad place to start because making people happy is probably also a good thing to do if you want to get reelected, for example. And then these are the questions I'm going to ask. How does an individual's incentive change over the course of an outbreak? And what are the consequences when they act on those incentives? And how should a government leader intervene? I'll just mention a few previous studies because there's a number of papers that have been published, some very recently, that have explored similar sorts of things. The top four here are maybe most closely related to what I'm going to present, although some of the others have some key elements of the economic analysis that I'm going to talk about as well. The main thing that differs from what I'm going to talk about in other results, or one of the main things, is I'm exploring how different kinds of diseases result in different outcomes. And so here's a preview of the main result. And there's really going to be two slides that if you sort of want to drift off, there are really only two slides that you need to sort of take home. One of them is the results slide, and that's what I'm showing here. We'll come back to it later. And the other is the slide explaining why the results are the way they are. So here's just a quick snapshot of what's to come though. So here's a disease outbreak, number of infections, or it's a fraction of the population infected actually over time. And it turns out that what happens is different depending on whether the disease is transmitted primarily by asymptomatic carriers, like is the case, well, maybe not primarily, but that's a good component of what's happening currently for COVID-19, versus if the disease is transmitted primarily by symptomatic individuals, which tended to be the case for SARS 2003. So I'm going to use these two things as sort of example diseases to put in the back of your mind, but of course they're not strictly falling along this dichotomy that I mentioned. There are obviously symptomatic individuals that spread COVID-19, and there were some asymptomatic individuals that spread SARS as well, but it's a useful distinction to keep in mind when thinking about these different results. And the main results are that as time progresses, there comes a point when it's in everyone's interest to have the government intervene and provide and compel everyone to stay home, despite the fact that people wouldn't have done that otherwise. And then eventually they're individually incentivized to stay home. And then we sort of back out of this process at the end of the epidemic. That's for asymptomatic transmission. If symptomatic transmission happens, then things happen in a different way. Individuals are incentivized to distance first. And there's actually a point in time where the government leaders, where the population, individuals themselves would have been better off if the government had intervened and got them to go back to work. And we can talk about the realism of that sort of assumption as I show you where it comes from. But that's the main sort of take-home message of these different kinds of transmission patterns result in very different incentive patterns over the course of an outbreak. So I'm going to go through the setup of the model now, and I'm going to go through a lot of the details of this because details are important in understanding where the results come from. So I'll first talk about the epidemiology. I'm going to imagine there are 4 states epidemiologically an individual can be in. They can be susceptible, they can be carrying the disease and infectious but asymptomatic, so C is carriage. They don't display symptoms, but they can transmit it to others. I, they are infected, they can transmit it to others and they're displaying symptoms. RC is a class where individuals have recovered directly from the asymptomatic class, and RI, they've recovered directly from the I class. And so I'm going to use these script variables to denote states. I'm going to use these variables here to denote the fraction of the population that is in each of those states. Big assumption I'm going to make is that once individuals recover from the disease, they're immune. Okay, so the flow diagram on this slide illustrates the structure of the model. You start out susceptible. Everybody, if they're infected, becomes asymptomatic. And then when you're asymptomatic, you can either recover or become symptomatic. And then when you're symptomatic, you can either recover, or what isn't shown here is you can die from the disease. Now, the other thing to notice is what I've put in the box here. That's a class of individuals that I'm going to call not yet sick. And that's going to be the focus of everything I talk about. And the important thing to note about that is in the absence of testing, an individual in any of those three classes would have no way of knowing which class they're in. And so they're in some sense, the same information state. If you have not yet displayed symptoms, you can't tell whether you're susceptible, currently carrying, or already recovered. And I'm going to focus on the behavior of those individuals for reasons I'll explain next. Okay, so that's the structure of the epidemiological model. As I said already, individuals have a single decision to make whether to distance or not. I'm going to call that delta sub I, where I is one of these different classes an individual can be in. So it's either a 0, 1. And what I mean by distancing is there's going to be this parameter alpha, which lies somewhere in the open interval 0, 1, which reflects the effectiveness of distancing. And in particular, if an individual chooses to distance, then their contact rate with other individuals in the population is proportional to 1 minus alpha. So the bigger alpha is, the more effective distancing is. I'm going to define D here to be the expected value of delta. It's the frequency of individuals in state I that are currently distancing. Okay, so delta I is an individual strategy, DI is the fraction of that class that are using the distancing strategy. And so the contact rate of the class of individuals in state I is just what I've written down here. A fraction of the population is distancing, in which case they have a contact rate 1 minus alpha, and a fraction 1 minus D isn't distancing, they have a contact rate of 1, and so that's the overall contact rate of that particular class of individuals. Now here's some things I already alluded to. I'm going to first assume that all individuals in the I class will distance, and that's either because they're sick enough that they stay home themselves, or because it's an obvious thing for a government to ask of people that they stay home. This is a very particular assumption that I think we can talk about what the consequences of relaxing that are later, but I think it's not a reasonable place, not an unreasonable place to start, given we want to draw out some of the qualitative features of these sorts of dynamics. So that means that the fraction of I individuals at distance, they're all distancing. I'm going to assume similarly that individuals who have recovered from the I class, none of them are distancing. And that's reasonable because if you've recovered from the I class, you know you've been infected. And so you know that you're immune. So there's no reason for you to stay home because you can't get infected and you can't infect other people. So really, I'm going to focus only on this not yet sick class for my analysis here. And I'm going to ask, what should their behavior do? What should their behavior be? And because an individual can't tell whether they're in SC or RC, they're going to have to use the same behavior regardless of which of those states they're in. So we're going to call those the not yet sick individuals, and delta subscript N here is going to be their behavior, either distancing or not, when given they're in that class. Okay, here's the epidemiological model in detail. So I'll just point out a couple of specific things of it, just so you get a sense of the sort of simplicity of the model. Again, it's meant to be a very qualitative sort of analysis. So the first thing here, this big lambda function here is the force of infection, and it's defined down here. The force of infection is the number of C individuals, the carriers, times their transmission rate, beta C, times their activity level, which is 1 minus alpha dN. And dN is the thing we're interested in figuring out. Plus the transmission rate from the I class, and all I individuals are distancing, so their contact rate is 1 minus alpha. So that's what we call the force of infection. And new infections are generated when that hits S individuals, each of which has an activity level that's 1 minus alpha dN as well. Okay, so all those new infections get thrown into the C class here, and then individuals in that carriage class can develop symptoms at a rate sigma, in which case they end up there, or they can recover at a rate gamma, in which case they end up there. And the individuals that flow into the I class, they can recover at a rate gamma. For simplicity, it's assumed to be the same, but we can talk about the relevance of that too. And they end up here. And then there are individuals that die from the I class and they leave the system. And I guess the other thing I'll point out is I'm interested primarily in a single outbreak here. So we're going to start the population where there are no I's, no R's, and we begin with a small number of individuals in the C class, but everybody else is susceptible. Okay, now the other thing I want to point out is that that's the epidemiological model, but because I'm interested in the consequences of an individual's decision, and because an individual's decision isn't going to influence the overall epidemiological dynamics, since the population is assumed large, we need to also keep track of the consequences to that individual of the decisions they make. And the way we can do that is by defining a stochastic process I'm going to call Y, and it takes on values in this state space here, these 5 different states. So you can think of this as the state of an individual. They can be susceptible in the C class, in the I class, or in either of the recovered classes. And we're going to set up this system of differential equations here that keeps track of the probability that an individual is in each of those different states over time. So we obviously need to start with some initial probabilities, and once we have those, we can use this system here to track the probability of an individual being in those different states as a function of the decision it makes about its distancing strategy. So notice that this system is coupled to the previous system because I can move as an individual from the S class to the C class by getting hit by this force of infection modified by my individual behavior. And so the system is very much analogous to the epidemiological system, except now we have individual behaviors in here, whereas this is the population level force of infection. So the two systems are coupled through that lambda function, that force of infection function. Yes, the other thing I didn't stress, but I should have, is that this decision of distancing here, delta, is a function of time. So I can make that decision differently at any point in time over the outbreak. And that's the question, how should I do that? Okay, so here's the pair of systems of equations, if you like, the population dynamics and the individual state dynamics, again, coupled to one another through this force of infection lambda here. So that's the epidemiology. Now I want to talk about the economics, and it's the economic part of this that people use as their incentive. So this is what they're going to pay attention to when they're making their decisions, or at least it's part of what they're going to pay attention to. So I'm going to define this function B, and that's the economic flow at any particular point in time to an individual that's making distancing decision delta at that time. And I'll tell you what A is here in a minute, but let's just look at the functional form that I have here. So A naught here is basically a payoff I get economically no matter what I do, whether I go out or whether I stay in. It's sort of a private payoff. And again, you can think of this in financial terms. I guess ultimately it has to be converted into a common currency, but this could also be rewards in terms of my enjoyment of different activities as well. So there's my private return, if you like, and then F here is a function that tells me my reward that I get for going out. This is the extent to which I go out, 1 minus alpha di. And the reward I get from going out is going to be composed of 2 parts. There's going to be a part that I'll call the public part, and that's just something that I get no matter what else is happening in the population, just from going out. Maybe I like going running or something like that, and it doesn't matter what other people are doing. I get a reward for doing that. But there's also a social component to the reward, and that's why this depends on A here. A is the fraction of the population that is available for interacting. And so A is defined by, well, 1 minus alpha D of all the N individuals are available, 1 minus alpha of all the I individuals are available, and all of the Ri individuals are available. So that's the number of other individuals that are, in a sense, out in the population moving around that I can interact with and get some reward from in terms of social interactions. And that's in this function F as well. And so F represents both of those things. In general, these are the assumptions that we would want to make of that it's positive at 0, meaning that I get some reward even if nobody else is out, and that it increases as the number of other actors out in the population increases. Typically what I'm going to do though is I'm going to use this very simple functional form. A1 here is that public return, my jogging return or something like that, and A2 scales the return I get from interactions with others, maybe because others out there increase my economic return or my enjoyment or both of those things. Okay, so that's the economic component of the analysis. And now I want to put all of that together into what I'm going to call the objective. And this is the thing that individuals are trying to maximize over time. So I'm going to define a vector X, which contains all of the state variables of the epidemiological model. And I'm going to define this quantity P, I bar J here. It's the probability that given an individual is in state J at time T, it's in state I at time tau, where tau is sometime bigger than or equal to t. And then I'm going to define all of these value functions, vi, that are functions of the state variables at each point in time. And that's going to represent the present value of all economic flow from that time all the way through onward in the future for an agent that's in state I. So any future reward I get has to be discounted by some discounting rate, and I've called that H here. And that could include a discounting, meaning that I care less about future rewards because maybe I'm not going to be alive for other reasons, or any other number of factors that might cause me to value the present much more than the future. So that's what discounting is. The bigger it is, the more I weight the future rather, or more I weight the present rather than the future. And I'll just walk through one of these. They all have the same sort of form. So this is the value at time t of being of an individual who's in the susceptible state at that time. So I'm going to sum up, I'm going to integrate all of the economic return from time t to infinity, discounting by that discounting rate. And then this is the return I get for the likely, weighted by the probability that I'm in each of these different states at time tau. So PSS is the probability I'm still in the S state given I started there at time tau. This is the probability I'm in the C state given I started in S, and this is the probability I'm in the RC state given I'm in S. So together, this is the probability I'm still in the not yet sick class given I started as a susceptible individual at time t. And this is my rate of economic return that I get for being in that particular state, given my choice and given what the epidemiological dynamics and the behavior of other people are over time. And then the other two pieces are similar. This is the probability I'm in the I class, given I started in S. And if I'm in the I class, I distance, so there's a delta equals 1 there. And if I'm in the RI class, I don't distance, so there's a 0 there. And all the other equations here have the exact same form, only they're missing terms because, for example, if I start in the C class, I can't go back to the S class. So I start with CC and RCC here and so on. But otherwise, all 5 of these equations have the same form. Now, what I want to do is look at an individual's value of being in the not yet sick class. And that's what's at the bottom here. And that's the thing they're going to care about. And that's the probability of being in the S class, given they're in the not yet sick class, times VS, plus the probability they're in the C class, given they're not yet sick, times VC, plus the probability they're in the RC class, given they're not yet sick, times VRC. And that's the thing that we're going to imagine individuals want to make as big as possible. So they're going to choose their behavior to make that as large as possible over time. Okay, so that's the setup of the model. That's what individuals are motivated to do and how the structure of the disease outbreak works. And now I'll just tell you a bit about how the analysis that we've done plays out, just because, again, it's important to see some of these details to understand where the results come from. So the first thing you could ask, I guess, is how are we going to actually figure out what the optimal strategy is here? And the way that this is typically done in models like this, so this is a differential game in technical terms, and the way that it's typically done is basically breaking up my decision over time into a series of individual decisions, where I'm going to consider the decision I make between time t and t plus dt conditional on I know what's going to happen in the future, regardless of what state we end up in. So I make a decision now, the system moves into some new state, and I'm going to assume that from that new state in the future onward, everything is determined. So I can figure out the consequences of any decision I make now, both in terms of my current payoff and in terms of the consequences of what happens in my payoff in the future. And so that's what this calculation here is meant to illustrate. So for any of the states in the not yet sick class, S, C, or RC, what I'm going to do is consider my decision in that little interval of time. So in that interval of time, I get a payoff, B times delta t, B is the rate. And then in the future, I get the integral from time t plus dt onward of everything else from we had in that previous slide. And I'm just going to simplify this integral here so that you can see a little bit more clearly the consequences of different sorts of actions. So again, here's my bit that I get from this current point in time. We can rewrite that integral in terms of those different v functions. So what we get is a weighting that discounts anything that happens in the future. And then this is the probability of me being in each of the different possible states in the future, states k, given I started in state I. And then this is the future reward I get from being in that state from time t plus dt onward. And if we just expand that all in delta t, it's useful to do that because you can see some very meaningful terms that pop out. So here's the piece that's due to my reward in this particular point in time. Here's the discounting that happens as a result of me not being interested in the future as much as the present. And then there's a piece here which has to do with the consequences of my decision. If I change my decision now in terms of my distancing, that's going to alter the likelihood of me being in each of the different states in the future. And so that's going to result in a different payoff depending on which state I end up in. So that's the consequences of my individual action. This here is the consequences of what happens epidemiologically. In the future, the epidemiological state of the population will be different as well. And that's going to have some impact on my future return. I don't get to control that because I'm only a small part of this big population, but a government leader could intervene and control that. And so we need to keep track of that as well. So if we just expand all that stuff out, and I'll just keep the pieces that mean something and just sort of ignore the pieces that don't, here's what we get. We get that piece that's due to the reward during this decision I'm making in this time interval. This is the probability that I'm still susceptible given I'm in the not yet sick class. Here's my activity level, and I get to choose that. Here's the force of infection I need to worry about, and I'm going to be hit with that if I go out. I'm going to potentially get infected. And then this is the consequence of me getting infected. Getting infected means that in the future, I go forward in state C rather than state S. And so this is the difference in value moving forward of being in state C instead of state S. And then this is that bit that has to do with the epidemiological dynamics of the population. So here's the susceptible pool. Here is their activity level, which depends on everybody's behavior. And here's their, the same force of infection. So it has the same qualitative structure as the individual piece. And then this tells me the consequences in terms of my reward, Vn, of increasing the number of people in the C category compared with increasing the number of people in the S category. So in other words, what are the consequences to me as an individual if some of the susceptible individuals in the population become infected right now in terms of my payoff going forward from the time T onward? And then there's a bunch of other stuff which I haven't written down because it's independent of my decision and it's independent of the decision of everybody else. And so it's the same regardless of what individuals' behaviors are. So all that really matters is what I've put in this little highlighted box here now, what I'm going to call the instantaneous reward. It's my reward during this time interval, the rate of reward. This is my risk of becoming infected and the cost associated with becoming infected. And then this is the cost associated to me with other people becoming infected at this time. And I've just defined these things down here. QS is this conditional probability that I'm still susceptible at the time of interest. Okay, and that's the thing that individuals are going to want to choose their distancing strategy to make as large as possible at each point in time. Now, the other thing I guess I need to say at this point is what sort of solution I'm looking for. And so I want to say something about that. So because what I'm doing, because my payoff depends on what I do and what other individuals do, it's a game, obviously. And so we can't just simply maximize something. We need to account for other individuals' behaviors. And typically what is done in situations like this is to look for Nash equilibria. The situation is slightly more complicated now because this is a differential game. It's a game being played out over time. And so we'd need to know at any point in time when I make a decision what the likely behaviors of everybody are going to be in the future. And so that's the first issue we need to address, is we need to somehow account for that. And typically what's done is and what I'm going to do here is look for what's called a subgame perfect Nash equilibrium, which just means that every point in time during this outbreak, I'm going to make a decision, I'm going to try and identify the decision that's a Nash equilibrium. And I'll define Nash equilibrium more precisely in a minute, but it's basically a strategy that if everybody else is doing it, I can do no better than to do the same thing as them. So that's the first thing. That's what I mean by solution concept. The other thing we need to talk about is how sophisticated these agents are in their ability to actually figure out what best to do. And what I mean by that is these quantities H and D here are very complicated things that take account of what's going to happen in the future and the likelihood of people behaving in different ways. And it's plausible that most agents aren't able, at least explicitly, to compute those things. Mathematically, we can do it by working backwards in time, but it's plausible that a lot of agents aren't able to actually do that. They may have a gut instinct for what these things are, and that might suffice. But it's plausible that they aren't perfectly rational in being able to completely compute those things. It's not a mathematical issue, but an issue of what we want to assume about individuals' capabilities. So we're going to assume that individuals don't actually keep track of those things explicitly. And in fact, I'm going to assume that they're constant over time. Now, an individual, even if they can't keep track of these things explicitly, might nevertheless have a perception of the cost of being infected and the cost of others being infected at each point in time. And that might change over time. It probably will, but I'm going to ignore that in the results I present, just because I think ignoring it, while though not necessarily realistic, allows me to bring out some important qualitative features of the structure of the model that we can then talk about how general they are if we relax those assumptions. So that's what I'm going to assume as well. I'm going to treat this cost of infection to an individual and the cost to an individual of others being infected as constants over time. I said I'd define Nash equilibria. There are two kinds of Nash equilibria that we need to talk about in the context of this game. And this is a Nash equilibrium at each point in time now I'm talking about. So if we have some payoff function, which is that instantaneous reward I talked about, for an individual that uses this strategy, given everybody else in the population, or there's a fraction dn of individuals using distancing strategy 1, then a Nash equilibrium is what I just said. An individual can, if everybody's using the Nash, so that's everybody using the Nash here, an individual can do no better than to also use that same strategy. Often there's a greater than or equal to here, but I've put the equal to case in what's defined next, which is the mixed strategy Nash equilibrium. And a mixed strategy is just maybe it's the case like I showed you in that diversification game, where there is no single strategy that's a Nash equilibrium. If everybody does one thing, I want to do the other, and if everybody does the other, I want to do the first thing. That should result in a mixed strategy, a strategy where different people are using different strategies, and that's defined as follows. D is some value that lies between 0 and 1, as it's a mixed strategy. The fraction using the distancing strategy 1 is a Nash equilibrium if, as an individual, I'm indifferent to whether I distance or not, given everybody else is doing that. So that's what I'm going to use. We're not going to worry too much about mixed strategies, but it's just useful to have that in the back of your mind. Now, I also didn't tell you, I presented a bunch of games, but I never really defined the nature of those games precisely. So I'm going to do that here as well, again, because I'm going to use these games to talk about some of the results. And so I won't go through all of this in detail because there's a lot of redundancy here, but let's look at this first one, what I've called the trivial game. The trivial game, where 0 here means it's a trivial game where nobody distancing is a Nash equilibrium. That means that I do better by not distancing. That's what this inequality says, no matter what anybody else is doing. So for all values of dn. And it's also true that if everybody is not distancing, everybody's better off than if everybody was distancing. That's what I'm going to define to be a trivial game where the Nash equilibrium is 0. And I want to contrast that with, let's go down here to the prisoner's dilemma at 0. Again, the prisoner's dilemma at 0, I'm going to define as a situation where I do better by not distancing. That's what this inequality says, no matter what other individuals are doing, just like the trivial game. But now it's the case that everybody would have done better if somehow a government leader had intervened and compelled everyone to distance. So that's the difference between a trivial game at 0 and a prisoner's dilemma at 0. Trivial game at 1 and a prisoner's dilemma at 1 just reverses those inequality signs in an obvious way. And then there are these coordination games. So I do better by doing the same thing as everybody else, basically. And the diversification game is sort of the opposite of that in a sense. So those are how I'm going to define these games. And now I'm going to, this is basically a statement of the main result that I want to convey. And then I'll show you a graphical illustration of the statement and explain why it is the way it is. So to state this theorem, I'm going to define this thing I've called an outer subsequence here. So let's imagine we have a finite sequence with an odd number of terms. I'm just going to define an outer subsequence to be a subsequence of S where I've deleted 0, 1, 3, 5, some odd number of middle terms of that sequence, okay? And then the theorem is stated here. If we look at the asymptomatic transmission case, so beta I is 0, no transmission from the I class. If D is greater than or equal to 0, meaning that there is a cost to an individual of other people becoming infected, or else no cost at all, then the sequence of games that occurs during an outbreak is an outer subsequence of this here. It starts with a trivial game with a Nash at 0, a prisoner's dilemma with a Nash at 0, a diversification game, and then it's trivial with everybody distancing, and then we back out of those things in the way we entered them. And it's an outer subsequence, meaning we can delete some odd number of things in the middle of that, potentially, depending on how big the outbreak is. Symptomatic transmission where beta C equals 0. If D is less than or equal to 0, then we have this, the sequence of games is given by this. So again, we start with a trivial game at 0, but then there's a coordination game. Then there's a prisoner's dilemma where everybody's distancing, but they would be better off if they hadn't been distancing. And then we hit T1 and we back out of that again in the same way. So that's the theorem. Let me just show you a schematic of that here. So this is the fraction of people infected. I've lumped all different kinds of infections together just for a schematic here. So there's an infection that happens over time. And then I'm considering asymptomatic transmission or symptomatic transmission. And again, roughly thinking of it as COVID-19 or SARS from 2003. And so the consequences of this are what I showed at the beginning. This was that slide I showed, which was one of the two main slides you should take home. And it's in the case of asymptomatic transmission, of course, you start out not caring about distancing, right? Because if there's very little infection, then you're not going to want to distance at all. Then the first thing that happens is there's a prisoner's dilemma where it would have been better, even though you don't distance and no one else does, it would have been better if the government had intervened and made everybody distance. And then we go through this sequence. Whereas in a symptomatic infection, as I said before, you get this kind of strange pattern where first you get a coordination game, then individuals are incentivized to distance, but it's a prisoner's dilemma where at this point in time here, it actually would have been in everyone's interest if the government had imposed a go back to work order. And so there's a difference in the structure of these things because of this different type of transmission. What I want to do is explain why that is, and that's kind of the last thing I'm going to do. So first, I'm going to show you a bit more about some results to show you what I mean by an outer subsequence of that sequence of games. So everything I'm going to talk about here, I'm going to assume D is equal to 0. It'll also be true if D is small enough, given that theorem. And what I've plotted here, if we just look at the left-hand side first, that's the asymptomatic case. The top here, I've plotted the fraction of the population in each of these classes. Here's the C class, the asymptomatic individuals, and here's the I class, the symptomatic individuals. On the bottom, this is again time, just like on the top plot, but this is now the cost to an individual of becoming infected, that H quantity. And so for this plot up here, I've set that cost at 2. So you can imagine, the way to read this is you trace through time for a particular H value, what you're going to expect to happen. So I'm tracing through time there. As I trace through time, the very first thing that happens is it would be best if the government imposed a stay-at-home order. Then individuals are incentivized themselves to stay at home. Then there's an interval where things get up to potentially a point where everybody distances, and then we back out of that. And you can see that as I increase the cost of becoming infected, as I go up on that axis, the interval of time over which these things happen gets bigger. And if the cost is low enough, there's no period of time in which any of those things happen. And so that's what I mean by deleting some odd number of middle elements of that sequence. Depending on what the cost is, I may never have some of those middle elements of that sequence of games. And the same thing is true over here in the symptomatic case, only the ordering of things is different. So the interpretation of this plot is the same. Only now as I trace through time, the very first thing that happens is individuals will be incentivized to distance, but they would have been better off if they hadn't, and then the government eventually is incentivized to ask them to distance and we back out of it. Same sort of thing though, with potentially dropping some middle number of those terms. So here's the other slide that you should take home, and this is really the only other main message here. This is a complicated thing I'll spend a bit of time going through because it explains why those results are the way they are. And the key to understanding that is to think about this force of infection here, this lambda. And that force of infection is different depending on whether it's asymptomatic transmission or symptomatic. In asymptomatic transmission, there's no transmission from the I class, so that term is gone. And what that means is if I look at the force of infection for the asymptomatic transmission, it's the same as the force of infection if nobody distances, weighted by 1 minus alpha d. In the case of symptomatic infections, so if I look up here again, now if it's symptomatic infections, there's none of those. And so if I think of what the force of infection is, it's the same no matter what anyone else is doing. So maybe a clearer way to say this is, with asymptomatic infections, the force of infection depends on what other individuals are doing, this dn. For symptomatic infections, it doesn't depend on what others are doing because the symptomatic individuals are already staying home. Now, this is a strong assumption, and maybe it's the case that my stay-at-home orders or forcing everyone to stay at home will also have some influence on the individuals in the I class. But as we can talk about later, I think the results are quite robust to relaxing the assumption in that way. So that's a key thing to understand, is that that force of infection depends on what others are doing in the asymptomatic case, but it doesn't depend on what others are doing in the symptomatic case, where others here are the individuals that are not yet sick. And so in the box here is this instantaneous reward. I get a constant reward no matter what I do. This is my activity level, depending on what I do at that point in time. And this is my activity payoff, my payoff I get from going out. So if this thing is positive, I'm going to want to go out. If this thing is negative, I'm going to want to stay home. And it's composed of my economic return, which depends on what others are doing. And it's composed of my cost, my epidemiological cost, which can depend on what others are doing if it's asymptomatically transmitted, but it won't depend on what others are doing if it's symptomatically transmitted. So in particular, F is always going to go down when a stay-at-home order is imposed, because once you force everybody to stay at home, everybody loses out economically. But the risk of infection is also going to go down if the infection is transmitted asymptomatically. And so overall, in fact, it turns out that this risk of infection goes down more than the economic return goes down. And that's simply because I get some economic return no matter what I do, whether we stay home or go to work, but my epidemiological cost is entirely driven by whether I stay home or go to work. So in the case of an asymptomatic infection, imposing a stay-at-home order increases the activity payoff. So it tends to make the payoff for going out better. In the case of symptomatic infections, this piece isn't affected by a stay-at-home order, and this piece goes down. And so for symptomatic infections, a stay-at-home order tends to make the activity payoff smaller. And that's the key to understanding why we get these different results in these different kinds of diseases. So I'm just going to walk through one example of this now to kind of highlight that. I'm going to zoom in a bit here and look at the asymptomatic case. So during an outbreak, the force of infection is tiny, then it potentially gets really big in the middle, and then it's tiny again at the end. So at the beginning of the outbreak, my activity payoff is very high. There's little costs to getting infected. There's little chance I get infected. And so I'm going to want to stay out. And then as time goes by, eventually the risk of becoming infected gets high enough that my activity payoff is zero right at this point. And that's where I'm going to want to switch potentially from going out to staying home. Before that happens though, in this region here, my activity payoff is positive but very small. Now, if a government official came in and said everybody has to stay at home, my activity payoff is going to get bigger, as we explained before, but I'm only going to get some fraction of that. And depending on the relative balance of those two things, even though I want to stay out here individually, if the government forced me to stay home and everybody else to stay home, we all would have been better off. That's maybe easiest to see right at this point here where my activity payoff is zero. Exactly at that point, if a government said, all right, everybody should have been staying at home, my activity payoff will go up. It'll be positive instead of zero. And even though I only get a fraction of that because I too have to stay home, a fraction of something positive is better than all of something that's zero. And so we get this prisoner's dilemma that happens in that point, and then we get this diversification game, and then things back out in the same sort of reverse order there. That's the case of the asymptomatic infections. If I look at what happens in the symptomatic infections, you can see there's an interesting difference in the factors that are at play here. So again, we have the same outbreak dynamics, only now what others are doing, the not yet sick individuals, don't influence my risk of infection. So early on in the outbreak, I don't have any risk of infection. My activity payoff is positive, so I'm going to stay out. And then as time progresses, eventually I'm going to hit this point where my activity payoff is zero if the force of infection gets high enough. Now, if you consider what happens just before that, like we did in the other situation, just before my activity payoff is zero, it's going to be very small and positive. Now, if a government was to impose a stay-at-home order, it's going to make that activity payoff smaller in this case because it affects only the economic component. So the government imposing a stay-at-home order here would potentially make my activity payoff negative, and then I'd actually want to stay home. And so that induces this kind of bistability here, where if everybody else is out, then the economy is really good, and I want to be out as well to take part in that and get the benefits of that. But if nobody else is out, then I also don't want to be out because there's not much to gain by being out. Then you hit this point where there's a prisoner's dilemma, but a prisoner's dilemma where everybody's distancing, but they would have been better off if they hadn't been distancing. And that seems a bit counterintuitive. And the reason is that, of course, in this interval, my activity payoff is now negative. But if the government imposes a stay-at-home order, it would be more negative. But if a government imposes a back-to-work order, it will still be negative, but it will be less negative. So I would be doing less badly if everybody was forced to go back to work in this interval than if everybody had acted in their own selfish interest and stayed home. And the reason is that when you force everybody to go back to work, it's not going to affect their risk of contracting the infection compared to the benefit they get from the economic return. So they're still doing badly in the sense that the risk of infection is bigger than their economic returns, but they're doing less badly than if they had stayed at home. And then in the middle, we have this T1 spot again, and then eventually things back out again in the opposite order. So that hopefully gives you some sense intuitively of why things work the way they work. I'll just finish off with one last result just to point out that when individuals act on their incentives, of course, this changes the nature of the game over time. So all of those results are assuming an unmitigated outbreak and asking what the nature of the game is over the course of the outbreak. If we let individuals act according to their incentives, well, here's an example where we have asymptomatic transmission. This is again a case where D is equal to 0. And now I'm looking at the situation where there's an unmitigated outbreak here, so nobody's doing anything. If individuals act in their own self-interest, then we can see we flatten the curve in this way. But if the government intervened, they would have imposed a stay-at-home order earlier because there's asymptomatic transmission, and they would have ended it later. Well, it's here actually. And that would have reduced the curve even more. And the interesting thing in this particular example is if the government had intervened, the force of infection would be maintained at a low enough value that it would never have been in an individual's interest to isolate on their own. There's always an incentive to cheat over this entire period here where the government has imposed this stay-at-home order, despite the fact that it's making everyone do better than if they had been left in their own sort of self-interest and ended up at a Nash equilibrium, which is up here. Okay, so I'll just finish with a quick summary then to highlight those main results, and I won't go through them in detail anymore here, but there's just these two important differences, or this important difference in these two different kinds of transmission, asymptomatic transmission and symptomatic transmission. And really what drives the difference in these two different situations is that when transmission is asymptomatic, collective distancing increases the benefit of going out. Whereas if transmission is symptomatic, collective distancing decreases the benefit of going out. Now, as I said, those are contingent on these assumptions, a number of assumptions I've made, but one of them is that the I class doesn't get affected by stay-at-home orders. But of course, you could imagine the I class's behavior also being modified to some extent by the stay-at-home order. These two patterns would still tend to fall out unless that effect is extremely strong. And then the other thing, I guess the last point I wanted to make is that the nature of the game, of course, changes as well by virtue of people acting throughout the course of an epidemic. And how that plays out is shown on that last slide. But there are other possibilities that would be interesting to examine that we're currently working on. Again, I'll finish there by acknowledging David, who is really the person who got me interested in all this and laid out basically most of these results to begin with. And I'd be happy to take any questions if anybody has any.
So, Professor Kumar, are you
Yeah.
able to sharing them? There's a bit noise
Sure.
in the background here.
Sure, go ahead. So if I'm sharing it, then maybe I can get to ask the first question. That's the only advantage of that. Troy, if you look on slide 19 or so, where you had a hypothesis that my action in an instant of time in t plus dt determines what's going to happen in the whole system going forward. Was that? Yeah, I think
so.
You might
probably this one.
Yes,
here.
yes, no, the previous one.
Or this one.
Yeah, that's it.
Yeah.
Is that a reasonable hypothesis? And I didn't really understand that hypothesis.
Well, it's not an assumption in the sense that what you can do is break the decision down into those independent decisions, provided you appropriately determine what the consequences are for those decisions from time t plus dt onward. So practically the way you do it is you'd start at the very end of time, whatever that might be. If it's a time goes to infinity, you have to think of some sort of equilibrium situation. But if there's a finite time, you start at that very end and you know what's going to happen in the future because the future's over then. And so you have a decision to make just at that instant in time. And so you can optimize at that final time, and then you step back one. And now I know what's going to happen at that final time step, and I can make my decision now conditional on what I know is going to happen in the future, given what I decide now. And you can step all the way backwards through the process to the beginning of the outbreak doing that. But at each point in time, you can think of the decision as being made in terms of what happens during that interval of time, and then the consequences in the future of that, which you've already figured out.
Okay, I think Masood had a question. Masood, go ahead. You're muted, I think. We still can't hear you.
Okay, Monsieur, we cannot hear you. Let me.
Okay, so the question is the following. So then, do you assume that end of the epidemic is fixed, or it could be random?
Well, it's not random, but it's not, I guess it depends what you mean by fixed. So it's not random in that there's no stochasticity, but it is also not fixed in the sense that, well, by the end, if you mean the outbreak is below a certain number, when that happens depends on what individuals' decisions over the outbreak are. So it's a deterministic model. So the outbreak doesn't really ever end. It goes asymptotically to zero. So if we define end by being below some threshold, then the time when that happens isn't fixed. It's determined by the choices that individuals make during the epidemic. But it is deterministic.
Okay. Then how many Nash equilibrium could have in your model?
Well, so I guess you mean at a particular point in time? So, you know, for example, let me go to this slide here. Maybe I'm misunderstanding your question, but in this slide here, for example, at this point in time, there are two Nash equilibria. Okay. There's a Nash equilibrium where everybody is staying home and a Nash equilibrium where everybody's out. And it's this sort of coordination game where you basically want to do what everybody else is doing. Yeah. Is that what you mean?
Yeah, exactly. Okay. And then the last for understanding, I am hearing for the first time economic component. It's really, maybe the other people could hear. I really appreciate that. For the first time I see it in the COVID, the economic component. And then this is the novelty here for me is the rate of economic flow. If I am correctly understood that if we don't have virus, then if you don't have virus, everybody not, yes, exactly. If you don't have the virus, everybody will not make a distance, and then the function B will be linear with respect to A0 and A1, A2. Am I right?
That's right. If you, that's right. So in most of the things that I've showed, I've assumed this functional form. Yeah, so if there is no disease, of course, everybody will want to go out, and the function is linear. That's right.
And then the differential game here is the presence of f, and it could be not linear. It could be some kind of the function, we should say. Am I right?
Yeah, that's right. So more generally, I mean, these are the assumptions that I think we would want to have in general for f. That particular choice obviously satisfies those, but there are others that are nonlinear that would also satisfy that. Some of the results, in particular, I think the results for the symptomatic transmission, I've been unable to generalize for functions of f that satisfy only these conditions.
Okay. Well, thank you very much. Thank you.
So Masood, this business about the economic impact is now a big topic of discussion. So we're having to figure how that plays into the models.
Yeah. So it's really interesting. I am hearing for the first time. That's why I am saying that.
Yeah. There's a question from Guihong Fan. You want to ask your question? Are you there? You're muted. Can you unmute yourself? No. Okay. So.
Wait. maybe I can ask a question if no.
Yeah,
Well,
sure.
Hello, can you hear me?
Yes, yes, go ahead.
Okay, that's great. So my question is that can you show us the page 29? You're talking about the activity paid off.
Yep.
Thank you so much. That's great. So I know the cost will be the chance of being infected, right?
That's right.
And I'm sorry. So the activity paid off. Can you tell me more about this? Is that like activity paid off? Is like my salary or the money I earned or whatever?
Okay, that's a great question. So there are two parts to it. So think of it as the rewards you get for being out rather than staying home. And that's composed of two things. You get some financial / satisfaction for being out. That's F here. But you also incur some risk of becoming infected, and that's this term here. And so the activity payoff is the sort of net consequence of being out, the rewards you get and the costs you incur for being out. If that's positive overall, then you want to go out because that increases your overall reward. If it's negative, then you want to stay in. And,
Okay.
and of course, that activity payoff depends on what everyone else is doing, because my economic returns depend on whether others are out, and my risk of infection potentially depends on whether others are out as well.
Okay. So the other part I can think, to be simple, I can think like the money I make. If I get out, I make more money.
Yeah, an easy way to think of it, that's right, is this is how much money you make, and this is how much you're willing to pay to avoid being infected.
Okay, got it. Thank you so much. That's great.
Okay. John Hong, you had a comment, question?
yes, Troy, if you can move to next page. Yes, so what does mean if it's purely under control, or is government control rather than individual control at the end of the outbreak? So you will see more cases.
What does it?
Now I see the red line is on top of the individual, the blue line. Is that the incidence or just coincidence, or is it always the case?
You mean out here, the red line
Yeah.
is higher than the
Yeah.
blue line?
Yeah.
Yeah, that's a good point. And thanks for bringing that up, actually. It has to do with this curious thing here as well. You know, so what happens in this example is here the government is incentivized for everyone's interest to impose a stay-at-home order. And here's where they shut it off. And when they shut it off, things go up again. And the reason that happens, and that's the reason why red is above blue here, is because in this analysis, I've assumed that the government has only one choice they can make. They let everybody, make or let everybody stay home, or everybody goes to work. What they should really do in this part is ask a certain fraction of the people to stay home and a certain fraction to go to work, and then it would stay below the blue. But in this analysis, I've assumed that they can only do this very coarse strategy where they say everybody stay home or everybody go to work. And as a result, there's a discontinuity in part of the model where that generates this corner here.
Thank you.
So Troy, that speaks to your cohorting business, right?
Yeah, that's right. That's right. So, I mean, I guess I made this assumption because it's not clear how realistic it is to impose, well, to carefully control the fraction of people distancing. But of course, that is at some level what's happening anyways. There's sort of nuanced levels of distancing by opening different sectors. So it's possible, I guess, to do that. But I haven't explored what the consequences of that are, short of just the little explanation I gave there.
Very good. That's a really interesting talk. I don't see any other hands up or people wanting to ask questions. If you have a question, please let me know. Okay, looks good. Okay, so thanks very much, Troy. It was a very interesting talk. And as usual, the materials of the talk will be posted on our website. Okay.
Thanks, Kumar.
Thanks very much. See you. Bye. Oh, we should applaud where we are. Thank you very much. You got it? Heard that?
Got it.